All right, hello and welcome to the stream. So the plan for today is to kind of explore what we can do with this flash cart. So yeah, I'm not sure if I should explain a little bit about the project first. Kind of wait for people to drop in and so on. But essentially what I'm building here is a flash cart for the Nintendo 64 using the Raspberry Pi Pico RP2040. And this PCB is, I kind of cleaned up the design that we did last time on the stream. And this time I added a SD card reader, micro SD card reader, and a PMOD connector. And these are all on the same net, so if you have the SD card connected, you cannot use this. But it's good for experimentation, so that's the reason why I did it like this. And I think this will be a good platform to sort of start exploring this as a concept. And also I have these 4 extra bus IOs connected as solder jumpers, so that you can connect these if you want to. So it's not much more to it. So it looks like this. I added the FlexiPin stuff. The reason why that didn't work on stream was because I didn't really think. So I had all of these tracks going over here. Hi. Thanks. All right. So I had these tracks going like all over the place, crossing these through-hole pads, because the footprint I used from the beginning was only on the top side. So I had tracks going over here. So when I changed the footprint, all of the holes kind of dug through the tracks. So that's why I got the different nets. So, hey, Arthur. Yeah, so this is how it looks. So I'm not really sure. Thanks for the follow. Not really sure where to go from here, and if we should start, exploring new ideas, or if I should sort of go through the design as it is right now. But in any case, I've ordered these PCBs, so they are on the way. They are already in production, because JLC PCB, they are just so fast. So I guess it really blew up, yeah. I should also mention here on the stream that I managed to get Super Mario 64 running on the breadboard, or like on the flying wire solution. That was kind of wild. I honestly didn't expect that to work. So just to do a recap, so what I did, maybe I should show a picture. Let me just bring up a good picture. Just 1 second. So first, I think after the stream, I managed to boot Homebrew using the flying wires solution, like so. There we go. But the thing is, here I used an ordinary Raspberry Pi Pico with the original 2 megabytes of flash memory, which is kind of limited. So with 2 megabytes, you can run Homebrew, but you cannot really run any games. So what I did was I soldered on a different flash. There we go. So I removed the 2 megabyte flash and picked the 16 megabyte flash, put it upside down, and then debug soldered the wires. You can see here. So yeah, this looks hard, but if you have a microscope and a decently steady hand, it is doable, for sure. And then I spent like perhaps 1 hour trying to get it to work, and it actually just worked. The issue I had was the Raspberry Pi SDK is sort of designed around the 2 megabytes of Flash. So Arthur, this might be interesting for you as well. So in order to access the full Flash, you need to change the OpenOCD configuration as well. So it's hard-coded in the OpenOCD config to OX2, like 2 megabytes. Like I wish this was like a variable that you could set, but it is not. Like if you set the variable, it will be set again by the script. So yeah, I copied the script and just changed this line, and suddenly I could flash and dump with OpenOCD. And then you have to change the linker script, which is somewhere. Maybe it's this one. Yeah, like so. This is also hard-coded, which is annoying. You can actually use variables here, but it is hard-coded. So here I changed it to 16 megabytes. So this allows me to link binaries that are 16 megabytes and that use all of the Flash. So there are 3 things you need to change. So there's this one, there's the OpenOCD script, and then there's also the confusing config, which is called something size, this one. But this only does one thing. You need to do 3 things. This only changes like the helper function for the Flash. It only fixes this stuff. So yeah, you need to. So yeah, a perfect PR would be that this one, or actually, yeah, I guess that this variable trickles down into the linker script in here, but then to OpenOCD, I'm not really sure how to do this. Like, yeah, having it as a variable that is not being overwritten would be nice. But still, I don't think the CMake stuff ties into this. So that's like 2 different things. But anyway, I found a way. And with that, I could flash the full Flash. So I put the 8 megabytes of the Super Mario 64 ROM in the end of the Flash. And then in the beginning of the Flash, I have the program, the actual code, so that I could program it multiple times without having to write the whole ROM multiple times. So that's what I did. And that's almost end of the story. So I had to fiddle around a little bit with the timings. So if you remember from the stream last time, we did wrong file. We have this little code here, the little cheat, where the very first word that is being read by the N64, we intercept that and change the value returned. So this is the bus speed configuration. So this configures the different registers of the bus on the N64. And this value is basically the number of clock cycles or something like that, that the read signal stays low. So high means long time, low means short time. And the original one is 12, OX12. So I fiddled around a little bit with this. I think I used 80, and that just worked like a charm. And yeah, just so we go full circle on the stream as well, I will show the video. 1 second. Here we go. And it's in a beautiful Twitter shitty quality. Ah, there we go, a little bit better. But yeah, it just turns on, and the demo runs, and the sound works, but not in the video because I messed up. But anyway, yeah, this is my living room. Here's a real N64, the flash card, the Pico, the original game here, and it just works. So there you have it. So yeah, what do we want to do now? So I was out riding my bike, and I suddenly thought about a couple of different approaches, and I thought, why do I have to choose? So I was thinking of just making like a bunch of mock-ups, and then we can sort of evaluate them as concepts and as we could try to build them. We could try to implement things. So I actually soldered up a bunch of PS RAM, the original idea. Oh, I'm gonna read chat. Yeah. So you need a full-size Pi Pico variation of the board probably, and license stuff is more pressing matter as it is public. Yeah. So I opted for the CERN open hardware license because yeah, I think that is decent. And regarding BSD versus GPL and so on, I think, I don't know. I have it as BSD right now, but we can always change it in the future because the code as it is right now is not a lot. And once we start to build an ecosystem around this with lots of features and so on, that will sort of add value. And if we change to GPL, we could do that. Yeah, it's been crazy. This is insane. It's really insane. And okay, I'm gonna read the next one. So a crazy idea. Hi, Jaku. That's a crazy idea. Replace the flash with PSRAM and add a tiny STM32 that will do SWD tiny code for SD card reading and start. You know, I had exactly the same idea, but I want to use a second Pico. So okay, I have so many ideas. I don't know where to start, but let's start with this sort of approach, the multi microcontroller approach, because that's really, really intriguing. So before I start to edit stuff, I just want to sort of close it down, and I have already committed everything, so this is just nothing. So thanks for the follow, Jaku. So let's see here. Right, just a second. I'm just gonna clean up a little bit. I saw your tweet yesterday and had to follow on Twitter immediately. Oh, that's nice of you. Cool. Are you familiar with the software on Twitch called Crowd Control? No. I'm just watching Twitch a little bit, but I'm not really. I don't really know about all of the cool features and so on. And also, you might notice that I have like the Twitch account is, I think it's partner, or the other one, affiliate. Yeah, affiliate. Because I just enabled it because it was fun. I wanted to see kind of what options you got, but I don't know really. Yeah, we'll see what happens with the channel. So what is the crowd control? Is it like blocking raids and stuff? Because I don't really mind raids. So let me just clean up a little bit. So the software allows viewers to send stuff into other players' games as they play them on Twitch. It supports real hardware on SNES and NES, but for N64 it's emulator only at the moment. Okay, that's really cool. That's really cool. Hype. Wondering if your N64 card could potentially be a way to get that working. Yeah, I don't know. In order to control the controller, you need to get into the PIF, the peripheral interface. So let me show a N64 schematic. Yeah, I think this one was pretty good. Open in new window. Oh, crap. Maybe here. There we go. Okay, so this is a schematic reproduction from someone, not Nintendo, who reverse engineered the PCB, I think. Okay, so this is the CPU, this is the reality coprocessor, this is the RAM, this is the peripheral interface, the flash card goes in here. Here's the video, here's the audio, and then here we have the PIF peripheral interface. So this chip is the one that goes to the controllers. So you see the P1, P2, P3, P4. And then you have the CIC stuff. The CIC is the security chip, so that goes to the cartridge. But yeah, so the thing, in order to send controller stuff, you need to sort of hook into these pins, which needs soldering, or you need to plug into something in the front. But just going through the cart is only possible if you have some hack, I think. Like if you patch the ROM and you do some fancy stuff, which is possible but requires work. So let me just catch up on chat. Sorry, it doesn't control the player. It reads write memory to the game's address space. Okay. It pretty much maybe. It'll need an Ethernet or Wi-Fi interface. So you can spawn enemies and give items and stuff like that. That's really cool. But in order to change RAM, so just to get the concepts clear here, to change the RAM, we need to hook into the RD RAM, which is basically not really possible. This is 250 megahertz DDR and funky. It's really funky. But we can patch the ROM so that whenever the game is asking for something at a specific address, it will get something different. That we can do. But RAM patching, that is a whole different beast. Maybe we can add an interrupt handler in the CPU and trigger the interrupt. So we add a patched interrupt handler, and when we trigger the interrupt handler, our code runs, and we could sort of perform operations on the RAM, like reading and writing it to the peripheral interface. That might be possible, but requires work. If you're following me. So I don't have an EverDrive or a 64 drive. I don't know how those cool cards work, like what kind of fancy features they have. Okay, cool, Jaco. So if anyone in chat has a 64 drive or EverDrive, do you know what kind of features that it has? Like, I know that you can save games and load games, but that is sort of emulating the SRAM part of the cartridge. But can it do like more advanced stuff? It's doable, but a huge undertaking on its own. Yeah, so I'm thinking, to be honest, just as an example, take Super Mario 64, for example. It's been reverse engineered to C code, and you can compile the C code back into the original image bit for bit, which is really cool. But that kind of allows us to add these kind of features if we would like to. The EverDrive has a debug USB port. If we patch the ROM, we can do some reading, writing, but it's very limited. Okay, good to know. The SNES interface we have is great. We can do RAM completely. That's also cool. So, yeah. So, I mean, technically, you could make an FPGA that hooks into the RAM expansion, and become a fake RAM. But that is like, no, just no. That's going to be so difficult. And yeah, the more I think about it, it's just a really bad idea to do that. I believe the interrupt stuff is the way to go. For NES, we have to do some approach that for the EverDrive. Wait, I have to read this one more time. Okay, so okay, the NES and N64 would work in a similar manner. The NES works because it's not nearly as powerful as the N64. Okay. So as an example, do you do like peek and poke at the RAM and change stuff at a certain address? That is like the high-level API to this. And then in order to implement that for an emulator, I guess that is really easy. And for hardware, it's yeah, in this case, really hard. But on the NES, I guess you can sort of hook into the RAM pins, and I don't know, won't there be bus congestion? Like if the NES accesses the RAM while you're trying to patch it and stuff like that. It feels like it could be kind of difficult. But I mean, you've done it, or it has been done. So yeah, it's cool to hear that. But I just see that it could be problematic to implement. But anyway, so for the N64, I think the approach that I explained just recently with the interrupt handler, that might be an approach. An approach. That way you can sort of have a tiny piece of code that the interrupt handler executes. And then from that code, you can sort of dynamically change the addresses you want to read or write. And then the result of that RAM contents is being sent up to the peripheral interface again. So you have like a message box going back and forth. So that's totally doable. But the interrupt stuff, I'm not really sure. There is this extra pin, which is the NMI, the non-maskable interrupt, which should trademark work as some sort of external interrupt pin. But then I've also heard that it was mixed up, or not, maybe intentionally mixed up. So the JTAG clock and the interrupt pin is something is weird with that pin. Or actually, it's the other way around. So it is the interrupt pin that goes to the JTCK, but on the chip, pin 57 is not JTCK, if I remember correctly, because this is not the NEC, not the NEC chip, it's the Nintendo variant, which is slightly different. So anyway, I'm gonna read. Sally, I have a meeting, but we'll be back if I have time. Okay, cool. Good resource. I'll save that link. I'll put it here. We can read that later. Conrad, you're on a slippery slope to a Patreon. Yeah, I don't know. Still really cool to see this project. I'm going to be following its progress. Yeah, nice. Nice to have you here. So yeah, feel free to drop by later on, and yeah, have a nice meeting. Yeah, so to be honest, Patreon and stuff, I don't know. I kind of, right now, I'm in a really good mood, and everything is sort of fun, and it doesn't feel like work. But at some point, I'm sure it will sort of drop over and feel like work. Because with the Game & Watch stuff, I sort of worked really intensely, just to give you a graphical view of that. This is Game & Watch. Like the Game & Watch stuff started here, and I was working literally every day, almost. And then I sort of lost interest, and it started to feel like work. And I'm sure the same thing will happen with this stuff, but right now it's really fun. Right now it's really fun. So I guess we can. Yeah, I'm gonna copy. I'm gonna clean up my repo a little bit so that we can start working. So I'm gonna add some stuff. I forgot to commit all of the assets. Let's see here. Git commit. Here we go. All right. So if anyone in chat knows CMake properly, like how the heck do you define stuff? So I was trying a lot of different things, and I don't know. add definitions. Okay. So I guess technically something like this. Oh. 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 So like this. Oh. -d. Okay. I don't know. I don't know if I should commit this or not. Yeah, I think hi, Brave to do. Nice to have you here. So I'm currently just cleaning up my repo a little bit. And we will soon start looking at the schematic and do some experimentation. So all right, this is gonna fail the CI build because I did some changes. Oh no, actually I didn't on this branch. I just learned that malloc doesn't clear the memory, the hardware. Oh, yeah. That's actually a good thing, I guess. I mean, sometimes you just want to allocate memory, and clearing the memory takes time, so choose your poison. All right. So yeah, but I didn't know it, and I was checking if it's null in a loop and figuring out. Okay. Yeah, exactly. There is a CLOC. Okay, so now I have a new branch, and we can totally destroy. So we can totally destroy this schematic. I'm on a branch, so that's good. So I think we're gonna go for subsheets for each concept. Hierarchical sheets. Let's call this concept 1. And then we can sort of move in what we want to have in that from here. So we're gonna need a USB connector, but that's sort of not super important. We're gonna need actually, yeah, let's just copy everything. So this one I think is gonna be a little bit. Let's start with a high level schematic first. So I'm just gonna move this a little bit out of the way. So we can use text. So we have the N64 bus, and then we have the N64 EIC pins. Let's have them here. So this is a high level diagram. So we need a Pico 1, and we want a Pico 2, Thanks for the follow. And then we need some flash. Small flash. And then we need PSRAM. And then what more do we need? SD card. I guess we can do something like this. So in order to free up as many pins as possible, I was thinking we do something like this. Okay, so if we just have this is like an image I had in my mind before. So just to explain what's going on here. The Pico 1 is the one that is connected to the N64 bus. This has the time-critical, really time-critical stuff. Sorry. And in order to have really good performance, we want to write our own Flash/PSRAM controller. And depending on results of our study, we could use the execute in place approach, where the Raspberry Pi's internal QSPI controller is fetching data from the external memory, or we make our own using PIO, because we have 2 PIO blocks, just Octus by 2 Picos together. Yeah, I mean, that's actually, so that's a really good point. So if we're using the external flash port here, then we get a lot of extra IOs here. We get all of, and we need code reset as well, but we get all of these. So that's 8, I think. 9, okay. 9, yeah, it is 9. So we need the code reset. That is mandatory. So let's just make this a little bit nicer. So the call reset needs to go there, but it also needs to go here. There we go. So the call reset goes to both the Pico 1 and Pico 2. The CIC goes to Pico 2. So just so we know the number of pins, we have 16 plus 2 plus 2, which is 20. That is this one. And then this one is only 1 pin. So we have 21 pins that we definitely have to connect. And then here we have basically 6 free pins, I think, for IO, clock, and chip enable. Which leaves us with 9 free pins. So we can definitely do OctoSpy. We don't even need, yeah, we have like 8 IOs and a clock. Sure, maybe we need chip select. So we get a synchronization. But you know, we could do some really cursed 7-bit spy because of PIO, you know. But it's really, really cursed. So let's not do that. So how many pins do we have here? Yeah, we don't even have to consider this small flash, but we need to connect this, right? So those pins are actually not free. They suddenly get allocated by the second Pico. So second Pico, we're consuming pins from the second Pico here. But here it's free. So the Pico 2 budget, we're down 15 pins, 16 pins. So yeah, let's put a 1 here as well, so we have it all in the same place. We have 6 and 1 and 9, so 16 pins. And then the CIC is 2 pins, so it's the clock and data. And then we have the cold reset. So yeah, what do we have? What was SD card? We had that here. So that was 4 pins plus 2. So that's 6 pins, I think. 7 pins because of the detect. Okay, so 7 pins. So we have 7 pins here. So let's do some math. We have 9 plus 1 plus 6 plus 2 plus 7. So that's 10 plus... I'm really bad at... is that 25? Yes. Just gonna ask Google. Yeah. So we have 25 pins, which is no problem. We could connect the Wi-Fi module or whatever, LCD screen. Okay, so we're using from 0 up to 24, right? Oh, okay, actually, we might not even need all of the 9 pins, but let's consider using all of the 9 pins. In that case, we have 25. Enough left for some couple of PS RAMs. Yes, but having PS RAMs on the Pico 2 doesn't... Well, you could load stuff from the SD card to the PS RAM and then from PS RAM to that PS RAM quickly. Like quick swapping between 2 games or something like that. I don't know. But yeah, that means that we have five pins left. Does that make sense? So if we think about use cases, so this is a really cool concept. Oh yeah, actually there is one more pin that I want to have. Let me just move this. This is gonna be annoying to draw, but let's do like this and call it the Pico 1 power enable. And that's using 1. So instead of resetting, I mean, it could also be the reset. It could also be the Pico 1 reset. Oh, wrong one. Oh, crap. So the idea, okay, let's see here. It'll make some complicated architecture. Need to split the load between the Picos, but how? With this architecture, right. In this case, the PS RAM will only be up to 8 megabytes, which is limiting the catalog quite significantly. quite significantly. I mean, we could, and this is complicated, but we could perhaps implement some sort of pass-through from these 9 pins. We have like a pass-through to the second PSRAM that could work. And then, this is... we could have like a binary BCD chip select. If you just make some math. So PSRAM is 6 pins. Chip enable is, 1 per chip. But if you have a chip enable that is BCD, or whatever you call it, like in binary, so you can have stuff like this is 5. Then we can have like a full bank of stuff. But of course, limited by the number of free IOs. So in this case, it's still, I don't know. Starry 2001. Hi. If I recall, max N64 ROM size is 512 megabit. Is that 64 megabyte? It is, right? Yeah. Yeah, right. So that is a lot. That is a lot. So going back a little bit to what we have today. This is like the board that is in production right now. In this board, why can't I open the 3? All right, I'm stupid. Now the modules doesn't work for me either. Crap. But anyway, on this module, there is a flash, and that flash could be replaced with a 64 megabyte flash. Let me just show you 1 second. 1 second. Oh, damn it. Okay. LCSC is a little bit slow for me right now. Just 1 second. There we go, finally. So this flash is the one that I'm intending to use on the first prototype. So I'm gonna patch Arthur's module. So if we go for the RP2040 stamp, and we go to solder party. Yeah, so here you see the module, and it has some flash here, but that is just a normal flash. So we're gonna replace this by desoldering it and putting this flash there instead. That way we will get 512 megabit. And another positive thing with this sort of larger flash is something you shouldn't underestimate, and that is erase speed. And here we have a block erase time of 0.22 seconds. So that is 64 kilobytes per 0.22 seconds. So that is 290 kilobytes per second. So if a ROM is 8 megabyte, that takes 28 seconds to erase, which is painful, I know, but less painful than, normal NOR flash, which usually is slower. So that is something to keep in mind. So anyway, in the board that I'm making, that is what I'm gonna do. So I was thinking of an alternative architecture to this. So just consider we swap out this with the 64 megabyte flash, 64 megabyte NOR. So this sort of resembles what we have today. And we connect this flash to the second Pico. And then we have this reset so that we can hold the Pico 1 in reset. And then during that time, we can mess around with the flash without the Pico 1 being confused or messing around with the IOs. So in that architecture, we will still be limited by the bus speed and latency that comes with the flash. But as you could see, I can still boot Mario. So it could be good enough, but we can always do better. So anyway, with that approach, we can have a second microcontroller that pulls stuff from an SD card, and we could, in this case, we don't really need this. So we get 9 more pins to do fun stuff with. So we could hook up this to something else. Second Pico can manage SD card and load portions to its PSRAM on demand. Yes? The problem with N64 games is that we don't really have any concept of banking, so you need to have everything, the whole ROM, accessible instantly, like over the whole range. But sure, it can help with the sort of preloading a second game and stuff like that. I'm looking forward to this. I tried to implement the flash card with the ICE40 and SDRAM. Oh, that's cool. But never got the gateway working. Got it reading the IPL, but not much else. Okay. But if it read the IPL, so you could see like the second read burst. Like first you get one kind of short read, and then you get this longer read. Did you get the second one? Because if you got that one, then it should have. It sounds like you got the checksum correct and all of that. With the CSE chip needs to be alive as well, I think. I'm not 100% sure about the details there, but it sounds like you got quite far, to be honest. Like once you get to that stage, it's only a matter of time to, like if you go back to the project, I'm sure you can probably get it to work. It sounds promising. So cool project. So anyway, so with this architecture, we have the 64 megabyte NOR flash, and this Pico could execute from RAM. So essentially, we could put it in reset. We write a tiny bootloader, bootstrap thing that loads the cart application, so to say, into RAM. And then the Pico 2 could reflash the first sector so it becomes the proper ROM. I know it's kind of janky and yeah, sort of backwards, but we could also do like JTH suggested before, that we go into debug mode on the Pico 1 and debug the core and put stuff in RAM that way. That way the external flash shouldn't be used at all by the code, which is a cleaner approach, but it uses 2 pins. But sure, in this case we have some pins to spare, so that could work. Oh, hi, look. Is that the 512 megabit NOR flash? The SSI only usefully supports 24 addressing. So for the next revision, okay, but it's a shame. Like really good input, because I haven't tried it. I didn't read the documentation. Like you've seen how I work. I'm a little bit too quick sometimes. But really good input. Okay, feature request taken. Awesome. Yeah, I mean, I don't know. It's really a niche thing, I guess, having to use huge NOR flashes like that. But still, it would be cool. So we're currently discussing like alternate approaches on how to connect everything together in order to facilitate, more features and larger flash. And so maybe we should go back to the idea we had before. But in that case, having the PSRAM here will also only be limited by the PSRAM size per chip. And sadly, at least I don't know of anything better, the largest PSRAM I know of in that form factor is only 64 megabit, so 8 megabyte. But we were discussing having sort of a pass-through PIO thing so that the Pico 1 accesses, so essentially having like a what's it called? Multiplexer, I guess. Like being able to select different PSRAMs with BCD, something like this. So that way we could have like a bigger array of, I don't know, it's really overkill to have a Pico like that, but having a second Pico would allow us to put the CIC on a separate chip, and that way we free up a few IOs as well on the Pico 1. So it's kind of overkill, but at the same time it's kind of cool. I like it. So if we explore that idea a little bit further, so in that case, we don't really need anything here. It could actually be a small flash. So here's a new concept. So this is basically concept 3, I guess. So the Pico 1 has a small flash which contains the firmware, which will run code. And then we don't need to connect this, so we get 6 more pins free here. And then here we have some sort of, let's call that PSRAM plus chip enable multiplex, or BCD. Or BCD is wrong, that is not the right word. But like binary encoder or something. So how many pins do we need for that? So we need 6 pins for the PSRAM, and then we basically have a bunch of pins for the chip enable, how many bits we want. Like if we want 3 bits, that will give us up to 8 different chips. So 8 times 8 is 64, but that is going to be costly because the PSRAMs are not cheap, unfortunately. They used to be cheap, but they aren't anymore. So I'm just gonna quickly find my link to the LCSC. So let's see here. So a couple of years ago, they were 0.5 euros each. And I have like a cut tape in the hackerspace with like 20 or so chips. But today, these chips go for $3. So that's 6 times more expensive. But in my mind, they are still at $0.5. So that's why I think about them so much. But that means basically we have 3 times 8. That's $24 just in PSRAM. So that's big oof. Big oof. Yeah, it hurts to read this. Like, holy crap. But yeah, that was in 2019. So I mean, it is a solution. I'm not saying it's the best solution. But then we only need 3 bits on this side. So here we have 3 pins for the chip select, which gives us 9 pins. So let's do the math again. So we have, let's see here. We have 20 plus 1 on one side. And then the reset doesn't count on the Pico 1 side. PSRAM is 6 plus 3. Right? So that's 30 pins exactly. So that is exactly on budget. Exactly on budget. because we have exactly 30 GPIOs. It starts at 0, goes up to 29. So with this approach, we use everything, and then here we let's put that aside. Let's think a little bit, because here we're gonna need the chip select pulled out properly. So we need PS RAM, and it's gonna be like an array. Chip select times 8. So this is 5 pins because we're not counting the chip select. And then we have the 8 pins. So yeah, that's 13 pins here. So that is good. So that gives us how many pins? 30 minus 18, no, 13, right? Was it 13? Yeah, so 17 pins. That is a lot. But we are minus 2. And then minus these as well. Oh shit, my budget brain. So 17, actually, let's do the math properly. 5 plus 8 plus 2 plus 1 plus 3 plus 6 plus 1. 26. That's still inside of budget. And we get 4 pins here. We have 4 pins for fun stuff. 4 pins, is that enough for SD card? I don't think so. We have 4 IO pins, but then we need the clock and this one as well. And optionally this one. So we are IO limited again. Fuck. So just to do a recap of what we just designed here. So we have the 64 bus going to the Pico. We have the cold reset going to the Pico. We have a tiny flash for a program. Reset is connected to the Pico 2. We don't need this pin. We don't need this pin. Because, yeah, we don't need it. So, away with you. So that means that we save 1 pin. And we are down to 25. SD card can be used in slow serial mode, less pins. That's a good point. I didn't think about that right now. But that means we have 5 pins free now. So we have actually 5 pins. Elias RM87, hi. Could you use the SD card in SPI mode? Yeah, good point. And I suppose there's nothing really limiting me to do that. And since this system is going to be relatively slow anyway, like it's probably, I mean, it's a compromise device, so to say. So yes, sure, if the SD card read is slow, then so be it, I guess. We could battery back the PS RAM so that if you load it, you could, keep it loaded until next time you want to play. I was also thinking about save states, or not states, but save games. And we haven't considered write on the peripheral interface at all in this design. So we could have like a large flash here, actually. In that case, large flash saves. And that way we don't need to redirect the write to the second Pico, but they're gonna be saved. They're gonna be saved here. That is, but no, I guess people want to have the saves to the SD card as well. Like, you back up your SD card and you have your saves. So that means that we want the large flash here. And we need to do an extra chip enable so that we could write to that one instead of the PS RAM. So we're up to 4 pins here and down 1 pin here. So this is gonna be spy mode. So how many pins do you need for spy mode? You need MISO, MUSI, clock, chip enable, right? So 4 pins. That's cutting it short, but could be done. Maybe chip enables can be multiplexed. How fast can we switch SRAMs? So yeah, so just going through this design first, just want to explain so we're on the same track. So in this case, the chip enable is encoded as binary like this. And then on the second Pico, they're converted into raw IOs. But you're suggesting that instead of having 8 pins here, we want to have an actual multiplexer chip so that we could have 3 pins here, like a multiplexer, like this to 8 pins converter, essentially. That is a good idea, really good idea. In that case, we're down to 3 pins here. And we need a multiplexer chip. Some 74 stuff. I'm really bad at that stuff. I don't know how that works. And then that's sort of that is tied here, if that makes sense. It's a little bit messy, but yeah, you have 3 pins going in here that is turned into 8 pins that goes to the actual chip select pins. Is this what you mean, JTH? I think, and in that case, we have a lot of 3 pins. So or is it like a binary encoder? Isn't it called like that? This is old school. Holy crap. It's a demultiplexer. Ah. So yeah, S0, S1, S2. So this is the 3-bit, right? And then we get 0. Right, and then on A we just have like a plus voltage. It looks like a scanned PDF. Yeah, you're right. And I think it is. I think it's like from the 80s or something. I have to look at it again. It says 2003, but that's probably when they scanned it. But yeah. But yeah, you're right. A demultiplexer is probably the right one. So it controls analog voltages. It doesn't matter for us. We want a plus 3.3 volt. It's bidirectional switch. Oh, thanks. I'll check it out. Oh, it's not the scanned PDF. Very nice. Feels modern. Does it say anything about the timing? Oh, yeah. Oh, this is perfect. Okay. So you have the 3 bits of inputs, which is exactly our use case. And then you have the 8 bits of outputs. Chip select inputs. Okay, this I don't really understand. What do these do? Oh, 5 volt. Okay, that's thanks. There is probably a 3.3 volt variant. Oh yeah, it actually says CMOS. But actually it says it works with 3.3 as well. So we could probably use it. But we probably want to use like the fastest there is. Like we want rise time and stuff like that to be really quick. Sorry. Previous one was HCT. Ah, okay. The scanned PDF, or maybe this one. HCT. Ah, you're right. Okay, okay. Yeah, okay, so this one. So I want to see rise time. What the heck is this? 1 microsecond? Are you kidding me? That is not fast. Our whole budget is like 200 nanoseconds. So we need to find like a fast multiplexer. I don't know. Let's go to Mouser instead and look for. Maybe even go to NXP or OnSemi. Maybe they have like a product selection guide. How do you even find the Jelly Bean stuff here? Maybe this one, Logic. Analog. Ah, okay. How do you even find those? Semiconductors. Product selection guide. Where are you? There we go. High-speed logic sounds promising. Flip-flop, fan-out, buffer, logic gates. I'm too stupid. Maybe we can look at this table. Ooh, fan-out buffer. Can we search for multi? Okay, no parts. Fan-out buffer. I've never heard that before. What even does that mean? We're speaking 14 gigahertz here. Okay, that's maybe too fast. Damn. The analog devices, they have some really cool stuff. Okay, 2 to 1, 1 to 4. Can we have 8? Okay, it's just finding stuff now. Why is this so confusing? Oh, we don't need a bus switch. We only need 1 pin. Okay, I'm gonna try on Mouser. Just do like this and say we want 1 bit. We want 8 outputs, and or do we want 8 bits? No, 3 bits, of course. 3 bits, 3 inputs, 8 outputs. Yes. Oh, thanks. I'm gonna check that out. This sounds way more promising. This is basically 500 megahertz ish, or 600-700 or something. per volt. So at 3.3 volts, we get 5. So 200 is my what? No, I'm confused. We get 5 nanoseconds. Yes. And that is definitely inside the budget, because we have 7.5 nanoseconds per clock cycle at 133 megahertz. So if the chip select rise time is 5, then we probably don't even need to wait one cycle after we toggle it. And it will still be way inside of the budget. So yeah, very good find. Thanks. Yeah, so let's write that down in the concept. So wrong one. Oh, that's a really good idea. So now that we know that this is a decent chip, it's fast enough. Can you buy it? Well, TME has it. Here we have some. This seems promising. Wow, it was not fast. Okay, that sounds decent, and the price is not that bad. We have it on LCSE. Oh, look at this. And it's way cheaper. Nice. Perfect. But yeah, maybe the rise time and so on is not the same on this one, because this is not the TI device. Oh, check it out. It's according to the spec. CD74 or Texas one. Right. That's fine. I mean, this I'm just looking at, like, is this chip generally available to buy? And yes, it is, and there seems to be alternatives, and we can get it from LCSC, which is awesome. And even the LCC chip is, according to the spec, well, I don't really like this. What the heck? 1.76 nanoseconds up to 139 nanoseconds. Okay. That had different times for HC versus HCT. Might want to double check. Yeah. Okay. So this was HCT. Oh, actually it's, wait a minute. Okay, so the proper chip also has this kind of wild maximum rise time. Yeah, you're right. Luke says that is an input transition. It's saying don't make input edges too slow. Okay. You're right. I should slow down. I should slow down. It clearly says input transition. So what about the output transition? Yeah. Not sure a 74 4051 is the right thing to use. Doesn't that tri-state the deselected? I mean, I could have pull downs in that case. Maybe that is not good enough either because of rise time. You need a clean deassertion. Okay, thanks. I'll check it out. Was HCT the good ones? This is a 5 volt. Okay, so maybe it was the HC. I'm not very familiar. I'm barely familiar with the 74 devices. I don't know anything. You need active low outputs. Okay, good to know. Thanks. So this one is operating inside of our range. It has the address and the outputs and then the enable stuff, which I didn't quite understand how. Okay, there are 2 active low enable, 1 active high. Okay, this sounds promising. Sounds exactly right. Okay, so it's the enable input. Okay, so I guess we just assert these correctly and then we input whatever we want. Okay, so what about the rise time? Okay, input transition rate. I guess we need to buy one and check it. No, here is actually switching characteristics. Okay. And I guess it's this one we're interested in, the transition time. So for 3.3 volt, I guess it's in this general range. So like 80 something. I guess we should look at 25 degrees, right? So maybe 15 nano. So again, what did we have? We had 7.5 nano per clock cycle. So that's 2 or 3 clock cycles that we need to wait before the chip select is stable. Which is perhaps good enough. But yeah, it's definitely a solution. Let's copy this. Okay. So let's say we go for this one. Oh, 75 AC. Okay, thank you. As you can tell, I don't have any clue about these 74 devices. I know of them, but not really anything about them. Okay, so it's basically the same. Or some timing. Okay, propagation. We want that one. But this looks much faster. What was it called here? It was called... Oh shit, I lost it. Let's go through this slowly. Input rise time. Propagation from AN to ON. So this is the active pin, or the input to the output, I guess. And that doesn't matter because it will be a constant one. Here we have the enable to ON. Okay. I want to see. Oh, right. A is actually the address. So these two are the interesting ones. And there we get 8 nano. Cool. At 3.3. So yeah, that's cool. Good to know. So let's save that one. Okay, so let's do the math again. So we had 21. So in order to have saves, we needed one extra pin here. We still need the reset pin. Yep. So we had 20 plus 1 plus 6 plus 4. Yep. That's 31. Oh shit. So how... Wait a minute. Piece RAM is not 6. It is only 5, right? Because chip select is one of the pins. Let's write it out. So piece RAM, it is 4 IO. It is the clock and chip enable, which we don't use, right? So that is 5 pins. And then the chip enable is the 3 bits plus the extra in order to access the flash. Oh, thanks for the link. So same design. It works at 3.3, yes. Input transition. Okay, here it's interesting. So this one, the PLH from input change. No, actually it's not the input change, it's the address change we want to see. Right? From ABC to the Y. Yeah. So that's data input, right? So from data input to output. Why don't I find it? Input is probably the actual input value, like which could be a 0 or 1, but we will have a constant. But anyway, these timings look really quick. What was it called here? Another one. PLH, propagation from address to output. So PLH. So do we have that here somewhere? It is this one. Okay, so input means address. Okay. So input to output is PLH. And where is the test result? I don't find it. Okay, I'm not seeing the value of TPLH. Why? Is it somehow here? No. I don't get it. Is it in a different document? Strange. I can't find it. I want this value, but I don't know where it is. So it could be fast. Oh, okay. TPD. What was that? Oh, TPD from ABC to output. Oh, okay, okay. So if we look at the graph, where is TPD? PLH. Well, it's probably something of this. I don't know. Oh, there we have it. Ah, PLH and PHL is the same as PD. Okay. Interesting. You need to read the footnotes as well. Damn it. So this one is really, really good. 5.8 nano. That's good. Thanks for the follow. So I think we have at least 2 chips that seems promising. What is this one? Including the Q1. Okay. So alternative D will Linux is this one. So just put it here. Okay, so let's go through it again. So we have the 20, we have 1, we have 4 plus 1, which is 5 and not 6. And then we have 4 pins for the chip enable, the encoded one. So we math this out. What do we get? We get 30, which is exactly inside of the budget. So with this design, yes, we use all of the pins, but it's okay. So on the second Pico, we have, let's just remove this and do it from start. We have 5 plus 4 plus 1 plus 2. So 5, 4, 1, 2. And then we have all of the PS RAMs on the same bus. And then we have the demultiplexer here. And then we have the SD card in SPI mode. And that is 24. I must have missed something. Or did we get so many free pins now? Feels like I have miscalculated something. 5, 4, 1, 2. 5, 3, 4. Because then we can run the SD card in real mode, or whatever it's called, the full speed ahead. So we have 4, 5, 6, 7 IOs. So change this to 7 IOs. And then we get 7 instead. It's 27. We still have 3 free IOs. That's so that's really cool. So I really like this now. This seems quite promising. What I'm a little bit afraid of is that the saves go to SRAM, which I believe, and I don't know this, but I believe it might be configured to run at a faster speed than the ROM, but I don't know. Maybe it doesn't. I haven't really checked. But the thing is with the let's go to am I drunk? No, that's wrong. There we go. And then we go to the PI. So SD mode. Okay, thanks. So the thing about the PI is that you configure, you have basically 4 different or 2 domains, and then a couple of subdivisions. And these can run at different configurations. So the cartridge ROM, this is the one that we're using right now. It starts at this address and goes up to this, which is, I believe, it's a bunch. I guess I can just do it like this. 251 megabyte. So technically, you can have a ROM that is 251 megabyte, which is only allocated using this partition of the memory map. But you could also have use this, and this, and even this, in order to use all of the address space, which is, I believe, 1.5 gigabytes or something like that. So that is interesting to know, but yeah, no games do that. But yeah, so what I'm slightly worried about is that games may configure the cartridge SRAM at a higher, like a difficult speed, so that we cannot be fast enough to process. If that is true, then this gets complicated. But what we could do then, now this gets really complicated. And that is that we put the large flash here, but we need a way to extract the save states from here to the SD card. So currently, in this design, the Pico 1 is like the master and Pico 2 is a slave, but we would need some sort of protocol, which is fine. I mean, this is SPI, so we could have a protocol over SPI so that the Pico 1 stores the, let's actually do that, because that might actually be easier. So the design is updated now. So Pico 1, which is connected to the N64 bus, it has a large flash, which will contain the maybe survey existing ROMs with some instrumented emulator. Yeah, that's a really good point. But we could still, I guess, just play with the idea. Let's just assume that saving to SRAM and loading from SRAM requires like a speedy, let's say it's as fast as the ROM, just, yeah, to make it easy to picture. In that case, we would probably not be able to process it here. But maybe, I have a vague recollection of someone telling me that the SRAM is actually slowly configured in many cases. So we might be in luck, and it might be easy to implement. Otherwise, we need to sort of patch ROMs so that they configure the SRAM memory area to be slow, which requires a ROM patch. Yeah, and I'm not sure if that is even, I mean, it requires work and it's annoying. So ideally, we don't want to do that at all. What could we do instead? Hey, I forgot. You know what? The Pico 1, you know what that has? It has RAM. It has actual RAM inside. You know? We could use the RAM of the Pico as SRAM. And then we could flush that contents through the Pico 2 to the SD card or wherever we want to store it. We could also store it in the large flash here. Like we have an SRAM cache, so that when you play a game, you sort of load the SRAM from the flash into the SRAM of the Pico, and then we just serve the requests from the limited but still quite big SRAM. Because honestly, how big was the SRAMs of these cartridges? I don't know. Super Mario 64 SRAM size. 32 kilobytes. Yeah, no problem. So we could definitely have that in the Pico RAM. So problem solved. Because we have the extra chip enable pin, we can serve, or I mean, we can communicate between the Pico 1, Pico 2. We could, we could store it on the large flash, and then we could page it down to the SD card if we want to, for backup. I think this is it. This is not bad. Yeah, let's write that. Pico SRAM. And then, of course, some of it is used by the stack and memory stuff. But let's say, let's use 128 kilobytes dedicated, right? So, and we're multi-chip, so if it's really, I don't know, we could use the second one as well, but no, that's gonna be nasty. But now I think, honestly, we have something. We have something here. This could be something. Now I'm thinking about the Wi-Fi module. So is there a way to multiplex between the SD card and a potential Wi-Fi module? And in that case, we need a bus switch, because this one doesn't have chip select. Like, yes, it says SS here, slave select, but it's just because it's mapped to the PMod stuff. So we would need like a 6-pin bus switch. We have 3 free IOs, so if we use 1 IO for the bus switch, we could change that to 2 free IOs. This one equals 28, and move this one a little bit. Then we up button, and 1 bit. No, okay. You write it like this. I don't know the terminology. But anyway, 6-bit bus switch. So then that uses 6 plus 1, because it's 6-bit for the actual bus, and then 1 bit for the select. And then you either get either this one or you get this one. But okay, so because this is an exploration, we could also do something really complicated, which requires custom firmware on the Wi-Fi module. But we could do this instead. And that way we wouldn't need this one. So in that case, we have like, SPI, QSPI, whatever, to the Wi-Fi module. And then we have a protocol that lets us speak to the SD card. But then the software will be kind of convoluted here, because we're going to go from SD card, or rather, we use the Wi-Fi, and then it downloads something from the network somehow and stores it on the SD card. And then it also tells the Pico 2 that, yep, we're done. And then the Pico 2 can stream from the SD card through the Wi-Fi module into the Pico 2 and go back to the PS RAM and load the ROM that you want to play. Technically possible. but now it feels like work, where the hardware team is like, yeah, we made a really nice design, and now it's only software left. It's no problem, right? But the engineering effort with this design is significant. Like if we go for this one, then we obviously don't need this one. So I'm just gonna move this down. And in this case, we would have three IOs free again. So I'm still not good friends with new KiCad. We have Wi-Fi module has own core with RAM, flash, and stuff, and software to manage. Yes, but I was thinking of, using like a standard Wi-Fi module firmware, so that I don't have to think. Like, I don't know. I'm pretty sure there are some standard protocols and standard firmwares for those, like ESP32, where you just, where you just like, become a Wi-Fi module and let me speak 80 commands or whatever with you. But of course, it would be more fun to write firmware. But like, look at this design now. We have one Pico here, we have one Pico here, we have a Wi-Fi module, we have SD card. It's a lot of firmware. So just building this will build 3 firmware binaries with 2 different tool chains. And we're slipping away from the simple design, but still, it will solve the problem. And oh yeah, let's do the fun thing, the business stuff. So, boom, we need 2x RP2040, which is $2. We need Wi-Fi module. That is like, let's say ESP32. That is like, I don't know, $5, something like that. Oh, sorry, ESP32 has ESP80, but that's as far as I know, just a UART. Could an ESP32 replace the Pico 2? GPS aren't that fast. Exactly. So just to recap a little bit, this solution here, this is sort of Pico specific and also really cool. So because the Pico has the PIO, we could do super fast transfers between the chips. But to be honest, we might actually use the bog standard SPI stuff as well. Like when we are in cartridge mode, we could do the fancy stuff, and when we are sort of in download mode for the saves, we could do SPI transfers from the normal C code. So we could be careful to hook this up in a way so these GPIOs are in this pattern, because this pattern matches the whatever it's called, the peripheral, the SPI peripheral. And then we can do like a DMA transfer from C code. So yeah, just going back again to explain the whole architecture now. So the Pico one, I lost my thread, so I'm just gonna start over again. So Pico one is connected to 64 bus. On the large flash, we are going to save SRAMs temporarily, but the SRAM it's also going to be 128 kilobytes of dedicated SRAM inside of the Pico. So we will be able to handle save games up to this size. Okay, and then in order for the Pico 1 to fetch data, right, we need to fetch data from somewhere. So we use PIO to very quickly fetch stuff from the Pico 2. So instead of Pico 2, we will have PIO firmware that it handles requests from this side and fetches from this side and responds back. So it's a kind of a complex chain here, but it might work. Using this chip, which is a demultiplexer, so we have 3 bits of chip selects. So these translate into 8 different chips that we can choose between. And we could use like the address bits. Like from the address, we could probably just mask out the most significant bits in order to pick the right chip. So just in case, oh, no, that broke. So we have 8 megabytes. And if we look at that in hex, it looks like this. And in binary, it looks like this, right? And we want to support up to 64 megabytes. So you just like look at these zeros. We have basically, it's rather ABC here. So imagine that this is the address that comes from the Nintendo 64. Then we can just map these bits straight to this chip, so that these bits directly chooses which PSRAM we're going to activate. So I think it could be a quite cool solution. Right, so continuing with the explanation. So now we have explained how the Pico 1 asks Pico 2 for data. Pico 2 will choose the right PSRAM based on these bits. It will access the PSRAM, get the data quickly, and then respond with that data. Then Pico 1 will take this data and put it on the bus. So it's a multi-stage rocket for sure, which of course will add latency, but maybe we will still save time compared to a large flash. But the more I think about it, right, so large flash is not good. We can write 16 megabytes of flash because, like Luke explained before, the Pico's execute in place flash driver only supports 3 byte addresses, which is 16 megabytes. So 16 megabytes is the maximum size for this solution. Of course, we could have a different flash on the external pins, but then we get into this whole pin mess again because we are limited again by this. This is what we have. Oh, did I remove that? That was not my intention. There we go. Yeah, so actually we have 3 free IOs, and just have a look here. What do we have here? We have stuff which could be interesting to hook up. So here we could actually hook up we have to choose which pins we want. So the non-maskable interrupt could be really cool to hook up, maybe, because what we talked about previously was just to do a small recap to what we talked about in the beginning of the stream. That was about using an interrupt with a custom interrupt handler vector inside of our code so that we could peek and poke at the external RAM of the Nintendo 64 so that we could do stuff like inject game states or game. Yeah, change the game state basically from the cart, and that could potentially, but I don't really see how now. Potentially be done via Wi-Fi, but I don't really know how, because imagine that we have the Wi-Fi which is connected to internet and we have multiplayer stuff going on, and then someone says I want to write in your memory. How will the Pico 1 get that? Like Pico 1 doesn't really know when it has enough time to perform a request and get it served. It like maybe when you end the read request from this time until like this time, you're basically free to do whatever you want. So you have a time window here where you're free to do stuff, but still it's icky. I don't see that being trivial. Okay, we really need to collect the data from actual games. What pins and what bus modes are used? Yes, you are definitely correct. And I know as a fact that these pins are sort of optional, because I can boot Mario. But I have a recollection, like vague recollection, that these are used for RTC purposes. And then there's some EEPROM. Yeah, I honestly don't know. I haven't done my research on this part. And also I haven't done my research on the NMI. I know that the official dev kit, the official N64 dev kit, has this pin changed here. It is changed here. It's swapped one place. Don't remember where I read that. I think it was right, because yeah, right. I have a strong memory that I've seen someone posting the difference of the board between like an official dev kit and a normal Nintendo 64. But I can't find it right now. But anyway, it's used for debugging purposes, and I believe, I don't know, but I believe that they sort of trigger an interrupt, and then they serve that request through a patched code or something like that. And through that, you could, once you're in interrupt context, you can, look at the registers and whatever you want, as long as you have like a small handler code. But yeah, those are definitely interesting. So I don't know. What do you think? Have we figured out something interesting here? Is this architecture something we want to commit to? I mean, we don't have to commit to anything. This is only exploratory stuff. But yeah, using this approach, we don't need any bus switch, and we get 3 free IOs, which is kind of nice. For SNES, for example, most carts can get away with middle part of a slot only. But then there's some cool Super FX games, right? Which everybody wants, and you have to go all the way. So need board data. Yes. Yeah, the people in the Discord of the N64 Brew, they are really knowledgeable, and I could ask and try to get some good information. So I'm sure some people have, full understanding of what this is and how it works, but I just haven't really gotten gotten there yet. I've only been focusing on the bus, this bus. But, yeah. All right, we were doing the bomb and somehow I got sidetracked. So 1 second, let me just dig up. Just digging up a link, just 1 second. So just to get like a decent bomb estimation, we have this cool ESP32 C3, which is the latest fancy module, I think. It goes for $3 at no volume, and at high volume it gets cheaper, so that's cool. So we're down to $3. And then we need this one, the MC something something. Let's just check Mouser. Okay, let's just say $1. Just so we get like a high ballpark. Then we need the SD card thingy. Oops. Like $1. It's actually not 8.5. Then we have the huge bomb part. We need 8 times whatever it was called again. Oh, there we have it. And this is gonna hurt. This is gonna hurt. So I guess here we can actually check this price. So it's 2.7 times 8, so it's $22. $22, yes. So total, and we need the USB connector, and it's like, I don't know, 0.5. So it's $29 for the bomb. And as you know, customer price is 3 times bomb. So we're at $100. So fuck. Fuck. It's still cheaper than EverDrive, whatever, but still $100. So yeah. 2 games are 512 megabits. So we could skip like okay. So if we go for like 128, then suddenly this is cut in half. So we're down to 15 there. Oh, sorry. I mean, so it's like $11. In that case, yeah, it's way cheaper. $18 bomb. And 18 times 3 is 54. Way cheaper. Way cheaper. We can still keep this one because I don't think it's like $1. And I don't think it will matter if we find like a 2-bit or whatever. It doesn't matter. Yeah, i3 it's nice. But with KiCad, it's kind of funky sometimes, you know. I don't know. Maybe I need a compositor update or something. Reminds me of Solitaire in Windows. But yeah, I guess it's a bug in KiCad or KiCad or bug. It's a feature, depends on how you see it. Anyway, so I think this one is the interesting thing. because this, doing 3 times BOM, you might, if you've never seen this figure before, you might think like, what the fuck? It says 18. How does 18 become 54? But trust me, it is never 18. Like, yes, the parts may cost this much, but you need to produce the boards, you need to manufacture, you need the PCB assembly, you need the packaging, you need shipping, you need fees, you need blah, 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 blah. So 3 times BOM is like, that is how you do it. Yeah, seems like it. Thanks for the follow. So yeah, I think this architecture is going to be a lot of work to write software for. And if we can build up a community of people who are capable of coding this stuff, I would, because I feel already now I feel that I will probably like never finish the software if I go for this complex solution. But if I have like people who are collaborating with me, then it could be done. JLC PCB offer pre-assembly. You can get a quote. Yeah, that's true. And they also have the Pico. Which is really nice. So you can actually search for the parts here. So, for example, you just search for this one. Check it out. They have 10K in stock, and it's a little bit more expensive, 1.3, because they are restocking it and blah, blah, blah. They need to pay fees and stuff as well. So it makes sense that it's a little bit more expensive. But yeah, let's see if they have the Wi-Fi module, for example. Or this one is more interesting, I guess. Okay, so you can actually use it. That's good. Oh, right, because they have the whole LCSC catalog. Okay, or maybe they don't, but let's hope they do. So let's see if they have this one. I think it's this one. Maybe you can actually search for this one. Okay, it's not stocked. Pre-ordered. Strange. Because it is in stock here. Oh, only 57. What the fuck? I thought it was... There were a few hundred before. Someone is buying right now. So anyway, I'm pretty sure we can find some ESP32 module. The important thing is that, we can code to it. Like, maybe we should sort by stock, to be honest. Like, go for the most popular one. Maybe this is the shit. Oh, no, this is the chip. We need a module. But yeah, it's like $3, and they have a bunch in stock, 16K. There are plenty of ESP variation. Yeah, you're right. But like a ballpark estimation, I think these numbers, yeah, so this maybe becomes 3 if you order via JLC PCB and so on. But then, yeah, if you use maker fabs, for example, to manufacture like a run, let's say I want to make 100 units, then they can usually go in the streets of Shenzhen and get really good deals and stuff. Yeah, I would recommend doing that. Like, if there are more than 5 people who wants a cart, then we shouldn't go for JLC PCB A, but instead like go for maker fabs and do like a run. But my goal here is not really to make a product, but more an enabler, so that people can DIY, build their own. And when I look at this design now, it feels a little bit convoluted. There will be QFN parts here, QFN. But the rest is actually easy to solder. So from a DIY perspective, the only downside with this solution is that, yeah, you get 2 QFN parts and you get some passives. We can make sure the passives are 0603 or instead of 0402. and 0201. Like, just make sure the components are a little bit bigger. And then normal people without microscopes can still build this. Like, make sure that this, for example, isn't like a BGA or wafer chip level, wafer chip scale package and stuff like that. So as long as I want to keep it hacker friendly, so to say, so that normal people can build it. It doesn't only have to be like a product. All right, so what do you think? Do you like this architecture? Is there something you want to change or do better? Like, we could perhaps, like, if we control the Wi-Fi module, which we probably will do, we could lower this. We could lower this to example-wise 5, and then suddenly we get 4 free IOs here, and we can connect the all rest of N64, and then we have a full. We have like a fully connected N64 bus. Geek at work. Hey, nice to have you here. What's wrong with BGA? Yeah, I mean, I don't mind, but some people do. If this gets traction, in the end, you can just AliExpress your own design. Yeah, I mean, to be honest, if someone, happens to make an AliExpress build of this, then I would just be happy because I don't have to do paperwork, and people can buy it from AliExpress, and everyone wins. So yeah, take my design, do stuff with it. Gorgo, hi. Have you accounted interrupt pin on calculations? Can you explain a little bit more? Are you talking about okay, let's see. NMI. Okay, it's used by 64DD to do any transfer. Okay. So now that you are here, and I know that you know this stuff much better, could you help me just understand? So actually, I don't have any idea how NMI works. So could you just try to explain a little bit what these signals do and why you need them? So I think NMI is just MIP CPU reset. Oh no. Okay, so it resets the whole CPU. So it doesn't just... So my idea, which is obviously wrong, was to sort of have a custom interrupt handler and sort of make it possible to interrupt the CPU and run custom code from our cart in order to do stuff like peeking and poking from the memory to facilitate stuff like game patching. There's another interrupt pin. Oh shit. Okay. Tell me more. So, am I missing something here? We have this one here. The OS event cart N64 NMI. But maybe these NCs are actually not NCs? Is there something hiding here? I guess pin 44 and 46. Where did they actually go? It's pin 44. Oh, thank you. Thank you for being here. So I guess if we trace that, it is this one. Okay, pin 44. This one. Oh shit, I lost it. This one. So okay, right. It's the one that is labeled JTCK because this is the NEC variant and not the Nintendo variant, but it's actually the interrupt pin. Oh yeah, okay. Because I have a memory of these pins being swapped. Yeah, exactly. But So I think this is the JTCK and this is the interrupt, if I'm not mistaken. But anyway, good that you're here. So let's just label that up then. So let's call that N64 int, I guess. And it was pin 44. But now, okay, so actually that is really good information. That means that the NMI, we can just say, screw you, we don't need to reset the game. Why would we want to do that? And instead, we want the actual interrupt. But that means that on the board that I just ordered, yeah, fuck. That is not being pulled out. So I'm gonna have to do a bodge somewhere. Yeah, fuck. It is this pin here. There's nothing here. I guess I can do like a tiny bodge wire here. So, yeah, all right. But really good information. Thanks. Bodgeable. Yeah, you're right. Everything is bodgeable with enough force, I guess. I use NMI in my FPGA flash card to change memory mapping to my bootloader. Oh, that is interesting. So oh, now I get it. That is clever. Because not a lot of games use the memory mapping stuff, right? Or if any. Like the whole memory map feature seems to be severely underused by games, if I'm not mistaken. But that is super good information. First iteration, no, of course. And I mean, I know that the first board is gonna be wrong. It's just how it is. Bootloader just loads menu from SD card to select games. Okay, I see. Yeah. Every N64 card works in that way. Okay, so, But why would I need to reset the game? Like, if I turn on the cart, all right, because after I select the game, I would need to reset the system. Otherwise, you need to press the reset button. That is annoying. That's a good point. Fuck. Okay, so we need this to reset the game, or reset the console. Because, yeah, let's say we start from scratch. You turn on the console, the bootloader starts, you get a menu, you select the game, you load the game, and then you toggle the NMI, and the N64 will reboot and load the actual game instead, right? If you can control CSE seed and checksum, then you don't need any bootloader. And I definitely can that. No problem. Because this Pico 2, so I don't know if you've seen the new architecture here, but we have one dedicated Pico for the 64 bus, and then we have a sort of memory bus here to the Pico 2. And the Pico 2 handles the CSE chip, but it also handles like a PSRAM pass-through and GPIO expander, essentially. By the way, are there CSE disable mods on N64? You mean changing the PIF? I believe there is an open source PIF. Or maybe it's even you who coded it, Kurgo. Wait a minute. Who made that? It's Ultra PIF. Right. Okay. Yeah. Okay, so that is the Brutzelkarte. But you're the summer card developer, right? Where is it? Yes. Okay. But why don't I find it? Isn't it called Summer Card 64? Here we go. Yeah. All right. So Yeah, nice. Okay, where were we? Yeah, so anyway, so we have this sort of bus, and the Pico 2 acts as a PSRAM expander. So we have multiple PSRAMs and we have multiple chip selects that go through a demultiplexer. And then we have a Wi-Fi module and SD card through the Wi-Fi module. And then we have four free GPIOs. We might, reduce this to 4, like do MUSI, MISO, clock, and chip enable. Okay, it got cramped. Okay, let's just make some more space. Like so. And then suddenly we have 5. So we can do the NMI. So if we do the math again, we have 5 plus 4, 1, 2. What? I must have miscalculated something. Okay, 29. How can it be 29? Did I miss something this time as well? Oh, okay. So that means that we actually have one free... yeah. So we actually have one free I/O. So, yeah, as I said before, there will be a lot of coding. First of all, just getting these chips and pass through with low latency to work, that might be a big headache, but it should be doable. Then you have this stuff, and like you have the save data, the SRAM. So we were talking about using the Pico 1 internal SRAM, like the normal CPU SRAM, as SRAM for games. And that way it will be able to handle those requests really quickly. And then it could page it down to the flash, or it could send it to the SD card through the Pico 2. Because we have one extra chip select pin here. We have the 3-bit, and then we have one extra pin that is like a dedicated Pico 2 communication thingy, so that we can talk to the whatever. And then inside of those packages, we can talk to the Wi-Fi module and or the SD card. And then we will need some protocol here, and we need... there's a lot of work, but technically doable. So for this whole design to make sense, we need to ensure a couple of things. Okay, by the way, we have a second Pico SRAM. We don't need that much PSRAM. I mean, it's not that big. It's only 264 kilobytes. So yeah, sure, we get the second one. So we have 500 and whatever it is. But I don't really follow what you mean, JTH. I mean, the PSRAM, like we calculated here, either we need 8 for the full 512 megabit games, or we go for 4. So I'm actually gonna change this because it's not correct. We go with 4, and we get 32 megabytes of PS RAM. So during boot, we need, we could have the bootloader in this flash, I guess. And then you get the menu. You see the menu on the TV. You select a game. Yeah, where does the game come from? Yeah, then this one has to talk to the Pico 2. It has to talk to the Wi-Fi module to get the SD card contents. Needs to create the menu contents. Yeah, I mean, Gorgo, we can probably reuse your menu and do some code reuse and try to borrow ideas, but it will still be a lot of work. It will still be a lot of work. But as a system, this might work. And from a BOM perspective, 54 is still, I mean, it is okay, I guess. If only the Pico had like 64 pins. That would have been nice. Yeah. All right. It's 1 a.m. here, but I'm still kind of fired up. This has been really fun. Yeah, it's been a lot of fun to explore ideas. And it's also a lot of fun with the chat that you're here and, giving me ideas and confirming, finding parts and stuff. Always interesting. So I actually soldered up a couple of PS RAMs, and I thought that maybe we should do some coding coding together with the logic analyzer to do like how fast can we perform requests. Luke just left too early. That was another fine feature request. Yeah. I mean, that would be so cool if they get so yeah, for people who are here who maybe missed it, Luke from Raspberry Pi told me that the maximum external flash size of the Pico is 16 megabytes because it only handles 3-byte addresses. Like it doesn't handle 4-byte address mode. So my initial idea, which with the board that I just ordered, was to use like a huge flash here, like a 64 megabyte flash, but that is unfortunately not possible. I haven't written menu yet. Okay. A couple of months ago, I ported an old project to a new platform based on Mac XO and STM32G0, and I lost interest in the project along the way. Understandable. It is how it is. And I honestly, this whole thing came from me sulking. Like, I was a bit pissed on the whole chip situation. God damn it, can't I even browse my own tweet? Anyway, I was posting, an old retweet of some FPGAs. Limitations sounds like a challenge. You're right. And I mean, we're pin bound, we are IO bound from the Raspberry Pi Pico, the RP2040. And that is why we have this sort of complex solution, which should work, but requires firmware, and time and will. And also, since this is a little bit more complex, the first iteration of the PCB might be wrong. We might need bodges and stuff. But it is how it is. It is hardware development. But it's also what makes it fun. I kind of enjoy the whole failure part of making hardware. Like if you've following me on Twitter since earlier, you might have seen like a bunch of bad hardware stuff, because I like to share when I fail, because I think that is sort of a nice thing to do, because hardware development is seldomly going on rails. Like, it's not like when you're coding and you just, oh, I made a mistake, let's just fix it, okay, no problem, and you just build and deploy again. But with hardware, you sort of have to either wait a couple of weeks and pay money, or you budget using a microscope, tweezer, and some thin wires. I found the tweet. So this is where it all started. So I was like a little bit in a bad mood, and like I found this old picture of my FPGAs, and I was thinking like, damn it, FPGAs are fucking impossible to buy these days. Literally impossible. Like, just to show you how impossible it is, you go here and type LFU5 or ECP5, and you go, you see like, oh yeah, they have on order, expected next year in May, on order, expected. And I'm like, okay, fine. What do you have in stock? Yeah, well, we have this one chip, which isn't actually in stock. Like, screw you, Mouser. What are you trying to tell me? So it's just hopeless to do FPGA projects. So that kind of bad mood was like, oh, damn it. And then I sort of found some other tweet about the RP2040, and then I was like, fuck, let's just do a schematic and see where we go. And here we are. It actually worked, and it's been fun so far. JTH, I'm afraid that chip internals just don't scale that easily. With 100-pin RP, yeah, I agree, and yeah, completely understandable that it probably doesn't scale. And also the PIO stuff is sort of 32-bit limited, and it wraps around the 32 bits and so on. But it would be cool to have like a dual RP2040. Like, imagine you have like on one like virtual bank you have 32 pins, and then you have the second bank with another 32 pins, and then you have the PIOs where you can sort of maybe you can select between the two different banks and so on, just to make it easy to do hardware. Because making it 64-bit and so on might be a little bit complicated. Like, this just feels like we could just, you just more or less, I mean, I know it's not that simple, but more or less just copy paste and just do more. And that would be cool. That would be really cool. I too started my project out of boredom and 64 drive unavailability. All right, mid 2020. And stock situation was very different. Yes, definitely. Like in 2020, there was still hope. Like the whole, I don't know. There are many intertwining limitations buried inside of the RP2040. They've really stuffed it. Yeah, okay. I think they should be really proud, though. It's really cool. It's really cool. Like, the more I think about it, I'm just, wow, it's nice. It's nice. And also, I remember when it was released and I read that it was dual core, I was like, when the heck am I going to use that? That seems so overkill. But it's super convenient. You can like put this CIC chip, which has this tight loop and just stalling for state changes on the GPIOs and stuff like that, and just put it on the other core. It's fine. It's perfect. All right, I think actually I'm gonna end it soon, because I really don't really feel like coding PSRAM stuff right now. It's 1 a.m. and kind of a little bit exhausted. But I think we've done some really good exploration, and we found some nice ideas here. And this could be like the proper cart, like the one that will be the more or less, yeah, not final of course, but you know, where we're going to eventually. And looking at the BOM price and so on, I know people will be disappointed, but yeah, I made like a ballpark estimate before of like somewhere between like $30, $40 up to $80, and this is still kind of inside that range, so it doesn't feel like too far off. It's possible to run CIC in a separate task with GPIO interrupts. Yeah, that's good point. Yeah. No need to waste the whole core. True. But you can. I mean, that's the beauty of the Pico. You have 2 cores, and you can just, if you don't need the other core, you can just do whatever. Yeah. All right, so I'm gonna wrap it up. I'll put this on a branch and commit it to the repo, and maybe add some links and stuff. But yeah, this pin 4044, that was really good information. Thank you. I totally missed that. All right. Yep. So thanks for hanging out, and it's been fun. See you next time. It's more of a question what to do with the other cores with 2 Picos. That's true. But I mean, I kind of like this, but it's also complicated. All right. Yeah. Thanks for hanging out, JTH, Gorgo, and everyone else. All right. See you next time.